Last clip, we saw that the matrix determinant is multiplicative. So in this clip, we bring that result over to the operator determinant. Now that we know that the determinant is independent of basis. So for an operator, t, the determinant of t is equal to the determinant of the matrix of t. So that was one of the big results that we've been working towards. So for the proof, so as in clip, I guess it was 10.A.6, wherein we proved that the analogous result holds for trace, namely that the trace of t is equal to the trace of the matrix of t. We can find a basis of t in which the matrix MT is upper triangular. Okay, so in this case, we saw that the lambda j is the jth entry, so in other words, the jth entry down the diagonal of this matrix A. Oh, and I guess I should say this is for A is my new notation for the matrix of T. So let's see. So then if we compute the determinant of T, it's going to be the product based on the definition for, whoops, not infinity, what am I doing? For operator determinant, it's going to be the product of the eigenvalues, and that's going to be the product of the diagonal entries of our matrix, and that's going to be the determinant of determinant of matrix of T by the definition of matrix determinant. Okay, and by 10.41, which we proved in the last clip, this holds for any basis. So 10.41 said it's independent of basis. Whoops. So this holds for any basis. Okay, so that establishes now that the determinant of an operator and the determinant of its matrix coincide. And then as a corollary to this, so proposition 10.44, for S and T both operators, we have multiplicativity. So determinant of ST is equal to determinant of S times determinant of T, which, if you like, is also, putting it back together again in the opposite order, determinant of TS. Okay, so the proof is mainly just reducing things to, well, it's exactly just reducing to previous results. So in other words, it's a proof by theorems. So for any basis, we have that the determinant of ST is equal to the determinant of MST by our previous result. So this is by 10.42. And then we can use the multiplicativity of M. So we can, the matrix for the product ST is the same as the matrix for S multiplied using matrix multiplication against the matrix for t. And so this goes all the way back to 343. And then we use the one that we just proved about multiplicativity of matrices. So now that we've got everything converted back into matrices, we can talk about this as determinant of ms times determinant of matrix of t. And so that's by 1041 that we just proved in the previous clip. And then we can go back again to operators using the result that we just had to get determinant s times determinant t. And so that's by 1042. And that gives it to us. For the latter equality, of course, you just repeat the argument with the positions of t and s interchanged, because determinant of t times determinant of s is definitely equal to determinant of s times determinant of t by commutativity of standard regular numerical multiplication.